All right. Thank you, Nick. And thank you all for coming. My name is Shuhao Fu. I'm a graduate student at UCLA, and this is a joint work with Keith Holyoke and Hongjin Lu. All right. So Nick has answered why relation is important. And here we want to ask, why is visual analogy also important? Because imagine when you first saw this robot dog, you have no idea the functionality, but when you make this visual analogy, map it to something you're familiar with, like a normal dog, you might guess that the functionality of the robot dog. Because visual analogy helps you find the corresponding parts, and which often imply corresponding functions. For example, the legs on dog and the robots are both used for movements, and so on and so forth. Another example would be, imagine when in early 19th centuries, and you first saw this huge giant machine with two wings, and how do you imagine that it can fly? And probably can make this analogy to a bird or eagle, as if you are familiar with. And you probably would think that the wings helps it to fly in the air. And how do people make this kind of visual analogy? And how far can we go with just visual spatial information? We took the inspiration from the Gardner's experiment in 1977, where she asked participants if a tree had a face or knee, where would it be? And participants would put markers mostly on these two locations. And similarly, if I ask you where are the robot dog's body and the legs, you probably would put markers also on these two locations. So we want to adopt that experiment, and we want to add some real objects to it. So here we use two realistic 3D datasets. One is Annual Pack Ultra 2 from Unreal Engine, and the other one is called ShapeNet Part, which is a subset of ShapeNet dataset, and we are using the chairs in the dataset. In our project, we also want to propose a quantitative measure of marker location accuracy and variability, and we developed a computational model that accounts for this kind of visual analogy. All right, here is a group of stimuli we use in our experiment. We have a bunch of different animals and a bunch of different chairs. And basically in the experiment, we have a source image where we have two markers already put on it. And on the right-hand side, we have the target image, and we have two markers. We ask participants to move the two markers to the corresponding location that forms an analogy. All right, we have over 150 choices for each participant, and we consider it as a nonverbal measure of analogical mapping, because the difference between the Gardner's experiment and our experiment is that we don't verbally express where we want to put the marker, but rather we have a source image like marked with parts already. All right, and we have two conditions. One within category condition, where the source image and the target image are from the same category. And we also have the between category condition, where the source image and the target image are from different categories. So the within category condition is what condition we consider is relatively easy for humans, because they share a lot of visual spatial information. And for between category condition, it's relatively hard, and we want to test human generalization ability. And we have a few possible results. We have the source image and the cities marked here, and we might have these red dots on the right-hand side from all the each participants. Each dot corresponds to one participant's response, and if they are clustered very closely, we will say it's a small between subjects variability. And if they scattered all over the place, we will say it's a large between subjects variability. How do we measure it? We take all the markers and we get the center of all the markers, and then we calculate the distance of each response by the participants to the center location, and then we take the average of it. For example, in this case, it might be like about 30 pixels. And here is some real results we collected in our experiment, where we have the source image, a horse, and we have the target image. So I plot this heat map from the participants, and the two heat maps correspond to the two markers. As you can see, participants very consistently put markers around the head of the dog, and here around the leg of the dog. And the mean deviation of the markers are 8.9 pixels and 7.5 pixels, respectively. And here's a between category condition where the participants will put markers somehow scattered all over the place, and the deviation is 18.2 pixels, and for the legs is 37.2 pixels. All right, we also plotted this violin plot where the y-axis is the deviation from mean location and the x-axis is the source category. We have two source category, animal and chair, and we also have target category. In this case, is animal, and we have this violin plot where each dot corresponds to one participant only. So we average across one participant's responses for this condition. And as you can see, the within category condition is much lower than the between category condition. And to show you how much the difference is, so for within category condition, the average is about 10 pixels. And here you see the circle on the nose. So here, the dog is about 200 pixels high, and 10 pixels is about the size of the nose here. And for between category condition, it's about 35 pixels in average, and here is about 35 pixels. All right, and also we have a very similar results when the target is chair. All right, and how do we model human behaviors? Here's an overview of our visual analogy model. We have two steps, where the first step is called visual module that builds a structural representation of each 3D objects. And then we have the second step, reasoning module, to map the two structural representation to each other. And the same color indicates that the two parts are matched together. Let's go over it step by step. Where in the first step, we have this 3D model 3D dog, and we sample a 3D point cloud around it. And then we pass the 3D point cloud to a deep neural network, which is called dynamic graph convolutional neural network. This network is trained with 16 rigid objects types, and it has never seen any animal before. So it's trained on the ShapeNet PAR dataset, and the dataset has rigid objects like cars, chairs, tables, and stuff. And we took the second last layer, which contains 64-dimension features. The feature, we think it captures the local geometric properties, and we use it as a visual features in our later structure. And then we cluster the point features into a bunch of parts, and ideally each cluster should represent a part of the object. And for example, in this case, we might have the blue one indicating it's a tail, and the orange one indicating is a leg. And we convert the clusters into a attributed graph, which is our structural representation, where the node attributes comes from the mean feature of the whole cluster of one cluster, and the edge attributes come from the spatial relation between two clusters. All right, and now we have the structural representation of the object, and we use a probabilistic and analogical mapping to kind of map these two attributed graphs together. Here is a simplified attributed graph where we have 3 nodes for dog and 3 nodes for chair, and the goal is to find this probabilistic mapping matrix where to map the 3 nodes to each other. And we have here, for example, torso has 0.1 probability mapping to the back of the chair, and the torso has 0.9 probability mapping to the seat of the chair, so on and so on and so on. You don't have to worry about the equations here, but the idea is to get this probabilistic mapping, we use a Bayesian inference method where the likelihood term comes from the similarity between two graphs. The similarity composed of both node similarity and edge similarity. And we also have this prior term, which favors one-to-one mapping. And here's a visualization of the mapping results, where, as you can see, here is a within category condition, like the back of the chair are mapped to the back of the chair, the legs are mapped to the legs, and also for animals, head mapped to head, and leg mapped to legs. And here we also have the between category condition. This result is much surprising as they don't share very much visual spatial information. And as you can see, the head of the animals are mapped to kind of top back of the chair, and the seat of the chair is mapped to the kind of back of the chair, back of the animal. Sorry. And now you have seen this heat map before, and we want to kind of visualize the model prediction on these two heat maps too, 4 heat maps too. So here, the cross are the model predictions for the 4 markers. And also we want to plot because in this violin plot, each star represents 1 participant, and we also want to treat the model as 1 participant and to see how the model performs and how closely the model is from human average. And the black dots are model predictions. And basically, we can say that the model prediction is almost 1 standard deviation away from human responses, even in difficult cases like the between category condition. And we also did a ablation study where we strip off the spatial relation, all the visual features, a model. So we use only spatial relations, all the visual features from the deep neural network. And here is the model prediction deviation to the human average. Here is a spatial only model, and here is a visual features only model. And here is our full model that we use both relations. All right, in summary, human can perform this kind of visual analogy, and human is very sensitive to shape similarity because when between category condition, deviation is much higher than the within category condition. And our model based on these local visual features and the spatial relations can account for human responses. And the 2 control models with only visual features or spatial relations perform worse in our prediction task. All right, conclusion is structural representation based on visual features and relations facilitate analogical mapping, and our probabilistic mapping handles uncertainty in a natural way. And to achieve human level understanding of images will require synergy between deep learning with big data and reasoning based on structural models. And my punchline is vision and reasoning are closely coupled so that seeing goes beyond pattern recognition. Thank you so much.